But
Oh,
somebody got it.
okay. So far, we've only got 2 people that have calculated it at all.
But
What do you got?
I calculated both and it got 1.055 times 10 to the negative 4.
You got what?
1.055 times 10 to the negative 4.
Okay.
Got it.
Now, 10 to the minus 4 what? Meters. Gee, that looks like 1.1 times 10 to the minus 4 meters, what that other guy gave us. Would you agree? Now, it is true you will get ever so slightly different. You said 1.05, which would round to 1.1. He said 1.1, which he also rounded. You'll get basically the same answer no matter how you do it. Okay? Everybody follow? Yeah. You will be asked to use integral calculus to find the diffraction pattern for either a single or double slit. Well, double slit diffraction isn't effective. The terms are vague. They're very tightly related. Okay? So, what do you think of this calculation so far? Is that reasonable?
It's fine, yeah.
Okay? Good. So, what does the next thing say?
The light machine should be like...
Okay, if the light is changed to green light, lambda equals 0.532, the diffraction pattern will change. What is the location Y of the first dark band? Aha! Now I'm not going to use any feature, I'm going to use a particular feature. Which particular feature am I going to use? The first dark band. Of all of these possibilities, which one is the first dark band? That one. That one is the first dark band. So I get 2 equations that describe that point. D sine theta equals lambda over 2.
Can we use the negative one version of it?
Oh, sure, I could use the negative.
Okay. Just checking.
And then you come out with negative something for y.
Okay.
I'll come out with positive something for y.
Okay.
And in this case, using the D that you got from the previous result, and the lambda you've been given, which one of these equations has only one unknown? The top one, yeah. So when you change the light, the D won't change, so use the D from the previous part of the problem, right? Separation between the slits. You put in the new wavelength and you get a new theta. That's the new theta that leads to this feature. And the y of that feature is related to the theta through the second equation. And then, ta-da! I got the y of the first dark band.
What are the units on lambda?
Nanometers, typically.
Micrometer.
Oh, yeah, this would be microns if it's 0.52. 500 nanometers is every bit. So since it's green, 0.532 would have to be microns.
Micro?
Yep, micrometers. Micrometers and microns are the same thing, yes. Can't hear you. Yes, I'm trying to solve for y. No. It was half 3 when you shined red light on the slit. You took away the red light. Green makes a totally different pattern. So when you change the light, you change the pattern. Okay? So if someone had not changed the light, then definitely the answer would be 1.5 centimeters for where that is. okay? But since we changed the wavelength, the pattern will change as a result. So the smaller wavelength will lead to what for theta? Smaller or larger theta? Smaller wavelength leads to smaller theta. So a diffraction pattern in green is squished as compared to a diffraction pattern in red. And where would the diffraction pattern in blue be?
Even squish.
Even squishier. Okay? Yeah.
The dismeter, the screen and the light.
Got it.
Absolutely, you got it. So, every time you identify a feature, you're going to come up with a pair of coupled equations that only go with each other, and they're only for that feature. Okay? They act as sort of a coupling. The first one is a condition on d sine theta that's either 0, half lambda, lambda, 1.5 lambda, etc. And then there's a feature relating y to theta, which is always tan theta is y over d. And they always come as a couple. You write them down together and you use them with each other. You don't then spread out and use the theta of this location as though it was the theta of that location, because it isn't, right? The theta to here is certainly not the theta to there. They're completely different things. So these equations talk about one feature simultaneously. One relates the theta to the y, the other one relates the theta to the lambda. And that's it. So what else do they ask? I'll make a sketch resulting from single slit. Okay?
Yeah. Well, 1 minute over. Hey, you know what? 1 minute time. That's too much of shit there, right? I'm getting kind of tired of it. You know what? That's why you're sitting between. Yeah, right? Exactly.
What does single slit diffraction pattern look like? That's part C, right? Make a sketch of single slit.
Yep.
What's it look like?
15 minutes.
At the middle point you have
It will be my name,
a maximum. Agreed?
Yeah. It wouldn't be still the same Y value, right? No, it wouldn't.
We'll talk about the y values in a minute. Okay? Now, in principle, well, what's the name for the function that I've just drawn for you? Sinc function. And actually this is sinc squared of UA over 2. Remember? It's the one that you guys have all been integrating every night before you go to bed. Okay?
Yeah.
And what was U?
U was 2 pi over lambda times x sine theta. Well, not
Right.
times x, times sine theta.
What cancels in here?
2.
The 2's. So, this is the sinc squared. What does sinc mean?
What does it kind of be at?
SINC function. What is it in terms of more familiar functions? Yeah? Yeah, sine of whatever's the argument over the argument. Okay, agreed? Now, where does this equal 0? Well, it equals 0 whenever the sine function goes to 0. Agreed? When does sine go to 0? Disagree, it was 90. It goes to 0 at 0, and at
180.
180, which is known as, in radians, pi. So pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. Yeah?
Good question. Is that sine theta A or UA?
U.
U.
We introduced this, when we did the Fourier transforming class, we did U.
Oh, U is a constant, that was
U is 2 pi over lambda times sine theta. So that's where the 2 pi sine theta in the numerator appeared and the lambda in the denominator. Okay? Now I'm about to get a condition. Once I get the condition, you'll say, why can't I just remember that condition? And the answer is yes, you can just remember that condition, but let me get there. Okay? Question? Oh, the lambda, that should be in micrometers with the units that are used. It would be 500 nanometers or 0.5 micrometers. Okay? So is everybody good with this?
That's all we have to draw, right?
Okay.
So you're gonna have to
Well,
write
that's all you would have to draw, but I want to go beyond the drawing, and somebody said, where are the zeros? And when I show you the expression for the zeros, you're gonna drop the derivation. But I want to go through the derivation. Because people are saying, is this related at all to the Fourier? And yes. Okay? So, where is the first minimum? The first minimum is when the crap inside the parentheses equals?
0.
No, the 0 doesn't count because it's 0 over 0 for a sinc function.
-1.
So, where does sine function have its first 0 other than the one with the origin? Pi. So when the stuff in the middle is pi, that's where your first 0 is. Okay? So your first 0 is when the stuff in the middle is pi. Agreed? So, what happens to the pi's? They cancel, bring the lambda over to the side, and this location is A sine theta equals lambda. Where's the second 0 of the sine function? 2 pi. So, set 2 pi on the left, and this one is at A sine theta is 2 lambda. Where do you think this one is?
Negative lambda.
Etc. So, you remember the feature analysis we did a few minutes ago? That's what you do here. You pick a feature, like this one. This feature is known by A sine theta is lambda, and also by tan theta is y over d. Because the tan theta is y over d is just geometry. And that will be two equations and two unknowns. This feature, on the other hand, is known by A sine theta equals twice lambda and
Tan theta equals y
tan
over
theta
d.
equals y over d.
Comment.
Okay? That's how you analyze single slit. It's the same procedure. Write down the conditions for the feature of interest. And then you have two equations and you solve them, and anything you ever want to know is there. Okay? Yes? Oh, I got the U from the derivation that I did in class.